morning. This is Dr. S.P. Harsa, Faculty of Mechanical and Engineering Department, IIT Roorkee. I'm going to present today the basic course of engineering science, that is the strength of material, in which the first lecture is the introductory lecture, in which I'm going to present the key features of the strength of material, like what are the forces, what kind of forces are being applied in the solid mechanics, if there is a pulling kind of thing is there, or the compression is there, or if there is no uniaxial, biaxial forces are there, then how these forces are being set up within the solid bodies, and due to these forces what are the internal resistances are there in the solid object, through which there are, you see, the stresses are there, the strains are there, the deformations are there. So all these issues I'm going to present here in this first lecture. This course is basically developed under the national program on technological enhanced learning. So as you see, this course comes under the engineering sciences, because in that there are lots of applications are there in that. So we can usually subdivide these engineering sciences into the various category, and the first category is the solid mechanics, in which there are solid objects which are interacting to each other. So we need to analyze those solid objects using the mechanics concept. So in that there are, you see, the two main branches. One is the statics, in which the static forces are being set up in the solid bodies, and the forces are there due to interaction. So, and the other branch of the solid mechanics is the dynamics, in which the dynamic forces are there, in which the forces are being, the time varying component. So when the object is in the moving part, we know that the dynamic forces are there and they are dominating in those conditions. So the solid mechanics basically dealing with the solid objects which are interacting. Then the second the division is there under the engineering science part is the fluid mechanics. In fluid mechanics basically we are dealing with that how the fluids are interacting to each other, and what are the molecules in this fluid mechanics they are interacting. That's what you see, there are various forces which are we can say that cohesion forces are there, or the combined forces are there, due to which the fluids are being confined to in the main object. And that's what you see, here there are various categories in the fluid mechanics also. If the fluid is very tiny or the thin is there, then we can say that the laminar flow is going on, in which there is no dynamics is there in which the fluid particles. Or on the second category we can say there is a turbulence is there, in which there are hectic motion is there, or we can say truly nonlinear dynamic motions of the fluid particles. So and then there is an the interaction, or we can say there is intermediate portion is there in between those laminar as well as the turbulence part. So these two the subdivisions of the engineering science is basically dealing with the different domain. One is the solid as well, another one is the fluid, and the third one, which is the heat transfer. So heat transfer can take place into either in the solid as well as in the fluid. So that's why you see we are categorizing this heat transfer into three main categories. One is the main mode is there, that is the conduction mode, which is a highly molecular phenomena. Like if you see if we have the different temperatures all across the solid, then there is a heat transfer right from one end to another end through conduction. So this is a purely molecular phenomena. Second, we have the convection, which is different than the first one, because in that there is a interaction between the solid as well as the fluid, and the convection takes place. And the third is there is the radiation, which is the macroscopic phenomena is there, in which the radiations are there and which is emitting from an object. And there are, you see, the Stephen's laws are there to analyze those things. And then the final, which is an important division of an engineering science, that is the properties of material, in which you see we are generally categorizing the materials into various the categories. But broadly speaking, then there are two main categories under this, that is the ductile material as well as that is the brittle material. In the ductile material, again there is the ductility is the property. So in that we are assuming that if a material is ductile, that it is pretty easy to extend, or it is pretty easy to just pull those material. But if we have a brittle material, then it doesn't have that kind of property. So what we are doing in that, it is because the brittle materials are good in the compressive stress, the compressive strength, so they are good the harder material. So based on what properties are there, we are always applying the material towards the application. So this, if you are dealing with the individual subdivision of these engineering sciences, then we'll find that it is not, we cannot fully analyze all the structure using the individual, concept of these mechanics, either the solid mechanics, fluid mechanics, or the heat transfer in which the temperature phenomena are there, or the properties of material in which you see there are various properties like the stiffness is there, like the damping is there, like hardness is there, toughness is there, the impact is there. So these are the properties, which always gives you a basic information that which material is applicable to what kind of application. Although you see there are close link in between them in terms of the physical principles, and that's why you see we are using these basics of, these are, we can say, these are the 4 basic pillars of the engineering sciences. And you see, if we want to make any kind of building, we need to know that what these interactions are there in between these 4 properties, or we can say subdivisions of the engineering sciences. So that's why we are saying that we need to put the basic link based on what the physical principles are there involved, and that is the nature is always saying that you see you need to maintain that what the physical setup is there in between these objects. And then you see we can go for the variety of the methods of the analysis which are employed for all these things, and that is you see the basic study of the engineering sciences. But here you see as far as this course is concerned, our main focus is on solid mechanics, that actually how these the solid objects are being set up, and how these forces are being well set up within those objects. Then if we are going towards the introduction, as I told you that as far as the subject is concerned, the solid mechanics is, as a subject, may be defined as a branch of the applied mechanics, because again you see what we are doing here, applied mechanics, and the applied mechanics we can go for solid as well as the fluid mechanics, but here it is a basic branch of the applied mechanics, solid mechanics, in which we are dealing with the behavior of solid bodies, as I told you earlier, subjected to variety of loads. Like you see, if there is a pulling, then we can say that technically we can say it's a tensile pulling, or the tensile load is there. If there is a compression, then we can say the compressive loading is there. But these 2 loads you see comes under the main category known as the uniaxial loading, because of you see if the load application is there, always you see load can be defined by the variety of the things. Like you see, if you are saying that it's a force, then force is nothing but the mass into acceleration, but the key feature in the force is what is the point of application. If the point of application is same, like if I'm pulling from both the side, this force is known as the load, that is the tensile loading, that means the pulling is there. If in uniaxial even loading, if I am saying that this is the compression, which is also acting on the same axis, we can say it's a compressive kind of loading. So these 2, either the tensile as well as the compressive comes under the uniaxial loading. But if it is a biaxial loading, means you see on the plane, like this x and y on a plane, if the load is there, then we cannot say it's a uniaxial loading. So loading can be of uniaxial, as I discussed, it can be of biaxial or triaxial, but we need to know that actually if these loadings or the forces are being there, they have to be satisfy the static as well as the dynamic conditions of the object, then only we can say that the object is under equilibrium position. So there are, as I told you, the variety of various types of loadings are there, like you see so if it is a uniaxial, then tensile as well as the compressive loading is there. If it is a biaxial, then it's a shear loading is there. If object is stationary, or if object is moving, then we can say it's a kind of torsional loading is there, like the shaft is moving, and on both the side, if the forces are there, the reacting couples are there, or the forces are there, you see we can say this kind of the torsional loading is there. This is usually subdivided into the further 2 streams, which is the basic thing you see. First is the mechanics of the rigid bodies, or we can say it is a simple mechanics in which the statics and the dynamics is there, and second is the mechanics of deformable bodies. That means you see one side we are saying that this is the rigid body in which there is a minimum chance of the deformation. Since the solid objects are there, they are interacting, but they are so rigid that there is no deformation occurs, and if there is no deformation, then there is no excitation is there. But if on the other side, if you are saying that the deformable objects are there, like you see most of the objects, they are deformable based on what the stiffness is there within this object. This is a unique property of the deformation. Then you see we need to know that actually how much deformation is there, it's a temporary deformation or the permanent deformation. So all this kind of analysis which is being studied under the mechanics of the deformable bodies. So first, if we see that under the introduction of this mechanics of deformable solids, which is also a part of, or we can say the category of the applied mechanics, is known by several names like strength of materials, mechanics of materials. Okay, and in that you see, like again, we are dealing with actually if there is a deformable body, then whether it's a temporary deformation, then you see, like under the temporary deformation there are variety of the laws are there, like there are this modulus of Young's elasticity is there, where the force is like proportional to the deformation, or there are other modulus of elasticities are there. So we are dealing with many of the things and many of the limits, like yield limit is there, proportional limit is there under the deformable bodies. But if it is a permanent deformation, then there is a kind of cracks are there or the spalls are there on the object, then we need to know that actually how much the stress or the force concentrations are there within those permanent deformation. So this is a different branch of the applied mechanics in which we are dealing with the deformable part, and that's why you see, like in all those strength of material or the mechanics of material, we are basically dealing with the stress, strain and the deformation. Okay, but if we are dealing with the other part, that is the mechanics of the rigid bodies, which is primarily concerned with the statics and the dynamic behavior, static and the dynamic behavior under external forces of the engineering components and system which are treated as the infinitely strong and undeformable. That's what you see, like if you are saying that the stiffness is too hard, means its body is so stiff that even if we apply the load it cannot be deformable, then it is pretty hard to analyze, because you see the forces are there, they are interacting. We can, you see, like set up those forces, but we cannot analyze using the stress, strain or the deformation concept. So this is a different part of the applied mechanics. Okay, and then you see primarily we deal here with the forces, motion associated with the particles as well as the rigid bodies, in which there is a stress, strain as well as the deformation occurs. So here you see, as I told you, that mechanics of solid is a branch in which there is a kind of deformable bodies are there. So mechanics of deformable solid is more concerned with the internal forces and associated changes in the geometry of the components involved because of the interaction of these objects. Okay, so here you see of particular importance, as like we are discussing with the geometry changes, because if there is an impact is there, always we'll find that there is a kind of noise. Why these noises are there? Because of the deformation. So how these deformations are being set up, whether these deformations are permanent or temporary, these kind of analysis which we are going to deal in this kind of subject. Of a particular importance which we need to give on the properties of material, what are the properties which we are using, either the ductile as well as the brittle material, the strength of which will always determine, always gives you the information whether the component will fail by breaking in the service, means how long it can bear those forces, or we can say whether these forces, what are the forces which are applying to those things, whether it can sustain those forces or not, or up to what. That's what you see, all those designs basically like use this kind of basic information. And the stiffness, this is a basic property, as I told you, for the deformable object, stiffness of which will determine whether the amount of deformable they will suffer, whatever you see the deformation object is there, whether it is acceptable or not acceptable. So in that, if you see, therefore the subject of mechanics of material or the strength of material is basically central to the whole activity of the engineering design, because in engineering design basically whatever the drawing is supplied to us, we need to know that you see whether those objects or the dimensions are sustainable to the load application or not. And that's what you see in that we in engineering design we always apply that what the material properties are there, or what kind of loads are being applied, or whether you see this material can absorb those kind of energies or the impacts or the load, or it can be safely operated or not. So this kind of like the interaction of the informations we are always using for the mechanics of material and for the basic of the engineering design. Usually the objective, like objectives in the analysis of any kind of analysis, the dynamic as well as the static analysis, will be determination of the stresses, okay, the internal resistances like strains, that how you see deformations are there, and the deflection produced by these loads. So these are three key terms in the mechanics of solid which we need to see, that what kind of stresses are being set up within the object, what strains are there, and how deflections are being taken place by these load application. And in that, that's what you see, like the theoretical as well as the experimental analysis is always gives you like the key information, whether whatever the analysis which you have done is real to the nature or which is applicable to the real nature or not. And that's what you see, like we are doing both kind of analysis here. And now you see, as like the stress is the key feature, as I told you, that we need to now define that what do you mean by the stress. Let us introduce the concept of stress, as we know that the main problem of engineering mechanics of material is the investigation of the internal resistance of body. Because you see, like if we apply the load, always body will react by the third law of the this Newton, that the reaction, like action reaction is there. So as you apply any kind of load, whether it's a uniaxial, biaxial or triaxial loads, always a kind of resistance will take place. So whether you see, like this kind of resistances can be well set up within the object or not. So as we can say that the internal resistance of body, or we can say the nature of forces which are being set up within the body, which can balance or not. If it cannot balance, then body will break. But if it can balance, whatever the applied forces are there and internal forces, if they can well set up within those objects, due to the external application, we can say that the body is well established under the application of load. Because load is always, you see, as I told you, that force can be like defined by two ways. One by magnitude, that is mass into acceleration, that is nothing but the load, and by the point of application, how these forces are acting on an object, and accordingly the resistance forces are coming, and we are saying that the intensity of the internal resistance is the stress. Okay. The internal resistance is per unit area, that is the intensity. And the external applied load, as I told you, forces are always termed as the loads. Now you see these external applied forces, which are the key generation of the these stresses, can be due to many of the reasons. Like first, the basic reason is due to service conditions. Means you see, like the objects are under the cyclic loading or the tensile loading, or any, like you see, as we are going towards any of the machine, if you are analyzing, we'll find that the bearings are there, the gears are there, the shafts are there. They are always under the different kinds of loads, and accordingly we are considering if we want to design the bearing, if we want to design the shaft, if we want to design the gears, or if we want to design any of the static part of the machine, we are always clearly observe that how these forces are being set up, or due to the environment in which the component works, whether you see it's on the normal temperature condition or severe temperature conditions, and because of these things you see the thermal expansion are there, or we can say later on that it's a thermal stresses are there, or you see through another reasons for the applied forces are through the contact with other members, and that is why you see the contact mechanics are there, and we are here concerning about that how deformations are being taken place due to this interaction. And then you see due to the fluid pressure, that you see if rho z h, if we are saying that rho is the density, z is the the gravitational acceleration, and height, up to how much height these fluid pressures are being exerting on an object, on and in that even the g is there, that is the gravitational acceleration or the inertia forces. Due to inertia forces also you see there is one of the basic reason that the stresses are inducing in an object. So now you see, if you come to that main point, these internal forces give rise to a concept of the stress. Therefore, we can say that the stress is nothing but the internal forces, or the internal intensity of the forces, like internal force per unit area. And if you see this figure, in this figure, as we have used the rectangular bar in which there is a axial pulling, and since it is a uniaxial pulling, so we can see that this is the P or F, this is the tensile force, which is the extension is there. And if you want to analyze those things, first we need to see that whether this object is under the stable condition or not. If it is under stable condition, that means whatever these forces, the axial pullings are there, they are well set up within those object. That means you see whatever the internal these resistances are there within this internal resistances are there within this object, they are well set up. And these internal resistances are basically due to this external this excitation force, that is P or F, which is there in terms of the Newton. And always we are concerning about these forces because of where the point of application of these forces are, and that's why we are saying that these are the tensile pulling. Like here you see from both ends, this is the tensile pulling. So if you want to analyze those things, first we need to make the cross section, and that's why you see in this this diagram we have shown here that there are two main parts. parts, and on both of the side, both of the end sides here, the P external excitation force is there, and due to this externally applied load, we have seen that if we cut those things at both ends through this x-axis line, these internal resistances are there. So each portion of these rectangular bar, either on the left or right side, is in equilibrium under the action of these applied load, the tensile load I should say, and the internal forces are always acting at the x-axis and just opposite to the applied load, and that's why you see we can say that this is the well established or equilibrium region. And if you are talking about the analysis of the stress or strain within those things, we can say that the stress is defined by the force intensity or the internal resistance forces per unit area, and hence we use the symbol sigma just to represent the stress, that is P by A, where A is the cross sectional area here, which is the rectangular area is there because the rectangular bar which we have used in the previous case. So here we are using an assumption that the total force or the total load carried by these rectangular bar is uniformly distributed all across the area, because if the load is non-uniform, then definitely you see the deformation or whatever the internal resistances are non-uniform, and then we cannot say that this object is in equilibrium position. But the stress distribution, which we can say that you see if the area is different at different regions, the stress distribution is obviously the different, maybe for from uniform or maybe local regions of high stress regions are there, known as the stress concentration. So if there is any abrupt changes there in an object, we can say that the stress concentration is more, and we need to design carefully for those kind of reasons. So if you are talking about the normal stress, then there is no problem because this is uniformly distributed because of the uniform force distribution in an object. If the force carried out by a component is not uniformly distributed, as I discussed during the stress concentration over the cross sectional area, we must consider the small segment or small area delta A, which carries a small load delta P, or we can say of the total load P, and that's why you can define the a small segment of the deformation. For that you see the small this stress is there, that is del F by del A, or we can say at a particular stress generally it holds true only when a point, or we can say for a small region, or we can say the infinitesimal region, the sigma is nothing but the limit of delta A tends to 0 del F by del A. So generally what we are doing here, because if we found that there is abrupt changes are there within the object, or we can say object is not uniformly rectangular or any shape, defined shape, what we are doing here, we are simply categorizing this object into various categories, and then we sum up those things, because you see we define the stresses for a small segment as we have seen in this, you see del F by del A. So we can again sum up those things by summing up of this limit of delta A1, delta A2 and delta A3 so on, and then accordingly we can get the total stress out of the whole object. Now you see, if you are going for the unit of the stress, because stress is nothing but the intensity of the internal resistances, the basic units in the SI system is Newton per meter square, or we can say the Pascal. Pascal is renowned scientist which gave the concept of the pressure, and pressure was also you see the force per unit area. So it has the same meaning, it is the internal resistances, or we can say internal resistance of the force, or we can say it is the internal intensity of the forces. That's why we can define those things by Newton per meter square or the Pascal, or if you go for higher side of these things, then it is the kilopascal, that is 1000 Pascal, or gigapascal, that is 100,000 megapascal, that is 100,000 Pascal, or gigapascal, that is a 10 to the power 9 Pascal, or sometimes it is pretty common to use the Newton per millimeter square, that is also equals to megapascal. So while this is a pretty common this unit is there in India, or in particular I should say the Asia or European countries, but US, you see in United States of America, they are using this pound per square inch, that is PSI, that is the FPS unit. Okay. And now you see this was the basic concept of the stresses. Now if you are talking about the types of stresses, there are two basic types of stresses. One is the normal stress and one is the shear stress. Normal stress means, as I told you, when the uniaxial loading is there, because of the uniaxial loading, whatever the internal resistances are there, per unit area, that is always comes out from the normal stress component, and that's why you see we are categorizing normal stress component by either pulling or the compression, because they are with the uniaxial part. And second, the basic stress is the shear stress. If they are not the uniaxial, if they have some sort of eccentricity, or these stresses are there for a plane where x and y planes are there, means here or here, you see, these stresses are being coming through the forces, we are always saying that it's a shear stress. So normal stress is a axial stress, shear stress is a plane stress. Other stresses are the derived stresses from these two. Like you see, like if you are talking about the normal stress, then as I told you, there are two components of that. By pulling, the tensile stresses are there. By compression, the compressive stresses are there. Shear stresses also has two components. Like one is, if it is a stationary object and you see the twisting is there, then the shear stresses are there because it is along the plane. Or if you see we have the torsional stresses, means if the object is moving, we have the torsional stresses. Another combination of these stresses are, we have the bending stresses, we have, and due to you see whenever the object is there, in the bending stresses we have both kind of things are there, the tensile as well as the compression, because both stresses are coming simultaneously at different points of the bending. Then we have like the another, that is the thermal stresses. Thermal stresses are always coming, which is not the part of that, but it is always coming due to the temperature variation, and it is being set up just to make the component equilibrium under the different temperature environment. So these are like the derived stresses, I should say, and some of the basic stresses are there, like the normal as well as the shear stresses. Just like as I told you, the torsional stresses, which is encountered in the twisting of a shaft, which is also a basic form of the shear stresses. So now come to the main part, that that how these stresses are there and how we can define those things. So first, the basic stress is the normal stress. We have defined the stress as force per unit area, that is the internal intensity of the resistances. If the stresses are normal to the area concerned, like you see here, if you see this, this is sigma 1 and this is sigma 1 towards this area, and this is sigma 1 towards that area. So if the stress is acting normal to the area concerned, so this is my effective area and the stress is acting towards the normal to that, that means this is there, you see, if stress is acting and this is my plane, you see, or this is the area of concern, I should say this is the normal stress, okay, and the normal stress is always defined by a Greek letter sigma, as I told you. So always we need to see that what is the point of application of the force or the stress, internal stress is there, internal intensity of the resistance is there. If it is normal, then we can say, or if it is perpendicular to the area concerned, we can say this is the normal stress. Okay, so this is also, as I told you, like known as the uniaxial state of stress, because they are acting at the uniaxial, because of the stress acts only in one direction, either the tensile or the compression. However, a state, whatever you see, this kind of state which is rarely exist in these objects. So what we are doing here, we are always going for the biaxial or the triaxial state of stress to define all those stress which are being set up within the component. Okay, so state of stresses where either two mutual perpendicular stresses are there in the biaxial, or three mutual perpendicular normal stresses are being set up in the objects. So we can define by this figure, like this is the above figure, this figure is the biaxial state of stress in which two forms of the stresses are there. In the x-axis, you see these normal stress is there, it is always lying along this line, and in the y-axis also this is always along this line, the this normal stress component is there. So sigma 1 and sigma 2 are the biaxial state, of stresses are there, the two forms are there, and the second one is the triaxial state of stress, which is, you see, like the sigma 1, sigma 2 or sigma 3 is there. So if you are considering all three axes, sigma 1 or this sigma 2 or sigma 3, all these stresses are being well set up in this object, and we can analyze accordingly. So either uniaxial, biaxial or triaxial, this is always, you see, if you want to define the real state of stress, always we need to go that which will give you the real true value of the stresses within those objects. Now you see, come to the normal stress component. In the normal stress components, it can be either, as I told you, pulling, or it can be compression. So if it is the pulling, like you see in this figure, the if this is a rectangular bar and if it is pulling from both the ends, and since you see like this is like the normal stress component is there, uniaxial part is there. So if it is pulling, we can say that the tensile stresses are being set up within this object. That means you see like if it is pulling, the internal resistances are so set up that if they will resist this kind of pulling. So that's why we can say that whatever the stresses are being induced in this object due to the application of this force, tensile force, these stresses are known as the tensile stresses. And simultaneously we can say that if the compression is there, this is also you see the uniaxial the state of stress is there. So if you are saying that actually these forces are being well set up within those things, we can say this is the internal resistances are so like opposite to this kind of compression, and they will always act towards the opposite to these action of these forces. We can say these are the compressive stresses. In these two like the forms of the normal stresses, like the tensile stress and the compressive stress, as we have discussed that these stresses are the normal parallel to these planes. So now our effective plane of the, or we can say this the matter of concern is this plane where these forces or the stresses are just perpendicular or the normal to stress these things. So always we need to be very careful that while we are like observing or analyzing those forces, we need to be very careful that how these applications are there, like how where they are applying, whether these here this one or towards that direction, or what is our like the plane of concern. So as either in the tensile or in the compressive, always we need to be careful that actually what is the plane of action is there, or what is the matter of the area of the concern is. So like these two the basic forms of the normal stresses. But if we derive those things, then again we will find that one of the derived stress is there, that is known as the bearing stress. Bearing stress is nothing, you see, like when one object, when two composite parts, that means two different objects are pressing against each other, it referred to bearing stresses. Like you see the two surfaces are mating to each other, and there is a well set up, like the forces are there in between the portion of these two objects. So they are in fact, like we can say these are the compressive stresses. But if we see the plane of area, then we will find that this is, you see, like in this figure, this is the plane of area or the matter of concern is there, where the stresses are just normal. You see that these are the compressive forces which are acting. So if we take the object or the soil, any of you see this is the basic phenomena is there in the this soil mechanics. So always what we are doing here, this object is always trying to press within this soil, and these bearing stresses are well set up within this contact region. So this is our contact region, okay, and these forces are there from the normal stresses. So that's why we can say the bearing stresses are nothing but one of the form of the this normal stress is there. And since it is the compression is there, so we can say that the compressive stresses are there. So if we want to analyze this kind of object, always we need to be careful that actually how these forces are being set up and how these stresses are distributing amongst these this contact area. So that's what you see, like if any eccentricity is there or any irregularity is there in this object, then we need to see that actually how these stress concentrations are being taken place at different parts, and how these internal resistances are there within this either object or the soil, because this is the contact region of the soil. And here you see these bearing stresses are forming all around this object, okay. So this is one form of the bearing stresses, and this is the derived stresses of the compressive stresses, one form. And then you see the another part, so one part was there the normal stress component, and the second part is there, that is the normal the shear stress. So let us consider now a situation where the cross sectional area of a block of a particular block of material is subject to a distribution of forces which are parallel. Now you see this is not normal, whatever the force is which is not normal to the this area concerned. Now if they are parallel, means you see this is object and the forces are applied parallelly to the this area of concern, then you see like then this is, we cannot say the normal stress component is there, then we can say that these kind of like the forces which are parallel to the normal axis always gives you a different kind of resistances or the area of concern, and whatever the internal resistances are coming due to these parallel forces are always different than the perpendicular forces, and such forces are always associated with the shearing of the material, because they are not uniaxial, they are at the different axis due to the eccentricity, and since you see they are running parallelly to the object. That means you see these forces are different at different layers of an object. So always you see we need to be careful that actually how these like the forces are being set up, and that's why we are saying that always it creates a shearing to these different layers at of this particular object. So these forces are associated with the shearing of material and are always referred to the shear forces. So shear forces you see like always creates some sort of shearing to the different layers of an object, and the resulting force intensity, that means the resulting shear force per unit effective area, is known as the shear stress. So you see this is the another form of the shear stress in which the forces are parallel. So here we can see this, we have this object, okay, since you see this here the forces are not coming perpendicularly, they are just parallel to these surfaces. So we have this effective surface here and these forces are acted parallelly towards that, and now this is our area of concern, these forces are going. So always within this object we have the shear stresses which are being set up within this object, and that's why you see here we are saying that these shear stresses are always plane stresses, because they are always towards this particular those planes. Means here you see like we need to concern this particular plane because they are all along this one. Okay, so that's why you see like we need to analyze those things, that actually how these shear stresses are being set up in these things, whether this is a uniform structure, then the shear stresses are all along uniform along this particular plane, this and this, or if any eccentricity or if any you see non irregularity is there in the shape or the geometry of the object, then we have to be very careful because these are the weakest area of the object, and we need to be very careful, and that's why you see accordingly we are taking the factor of safety for this kind of stresses. So shear stresses are more, I should say, like the dangerous, because you see they are running parallel to the layers of an object. Then you see like if we define the shear stresses, then the like as I told you, the resulting force, the shear force intensity, which is known as the shear stress, is the mean shear stress, and which is equal to this P by A. P is the internal like the force resistance, this resistance force is divided by the effective area, and it is always denoted by tau. So P is the total force, as I told you, the shear force I should say, and area is the effective area under which these forces are being acting. So as we know that the particular stress generally holds a good part only at a point, therefore we can say like the shear stress at a particular point is limit the tau, which is limit del A tends to 0 del F by del A. So this is you see like the small segment of force divided by the small area. So generally you see this this equation is valid where you see if we found that irregularities are more and we are segregating, or we are separating those individual components, because you see if the strong region is there, weakest region is there. So what we are doing here, we know that the forces are whatever the force distribution is there within this object is different, then we have to be very careful that actually in the strong region how much force distribution is there, for the weakest region how much force distribution is there, and what is the area this matter of area concerned. So accordingly what we are doing here, if we are saying that if we have an object which has if we are categorizing an object in 6 different like the steps, then what we are doing here, we are always calculating tau 1, tau 2, tau 3, tau 4, tau 5, tau 6, and in all these taus always we are assuming that whatever the area of concern is there, they are always to that particular effective area. So that's what you see, this approach is known as the infinitesimal part, because you see in any of the like engineering sciences we are doing, like you see in thermodynamics, basically whatever those like the processes are there, like this isochoric process, isobaric process, isentropic process, all these processes are if we are going realistic, then we cannot approach really, because the real nature is always against those things. They are not like the reversible phenomena if it is a real process, but always we assume that these processes are really occur in the nature and they are reversible. So what we are doing here, we are always taking the small segment, and within this small segment we assume that that these processes are correctly applied, whatever you see. So similar concept we are apply here, that whatever the small region is there, within this small region we assume that whatever the force application is there and divided by whatever this this effective area is there, if we sum up those things by integrating all those the small segment, we assume that this stress distribution is uniform, and because of this stress, whatever, either is irrespective whether it's a normal stress or it's a shear stress, we assume that this stress is well set up. If you sum up those things, it will give you the average normal as well as the average shear stress component. And that's why you see, we are always applying that if it is a delta F by delta A for a small segment, it always limit A tends to delta A tends to 0, and this will give you a small shear stress component for a segment. And if you sum up those things, then you will get the full stress component. So if we, that's why you see, as we discussed that actually this shear stress is always denoted by a Greek symbol tau, just like you see in the normal stress component, it is always either irrespective of the the tensile stress or the compressive stress, which is always being denoted by the sigma part. So it is used to denote the shear stress. However, it must be borne in mind that the stress, the resulting stress of these things, any point in the body, is basically resolved into two components, because as we discussed that there are two main components are there of the stress, normal as well as the shear. So sigma as well as tau. So how these the stress components are being acted separately as well as the combinedly, how the interaction is there of these, you see the normal as well as the this parallel stresses, I should say parallel because of the parallel forces are there in the shear. So how the interaction is there of these forces, and how the molecules of the matter they are affected by the interaction of these stresses. This is really a matter of real the matter of concern to analyze under the mechanics of material. And that's why you see these two, if you want to analyze any material, then we need to resolve these two stresses. One is the sigma, one is the tau for normal stress as well as the shear stress. One acts perpendicular, the normal stress, and other one is the parallel to the area of concern, as it is clearly defined in the following figure. So you see, if you see this figure in the previous figure, then you will find that you see here that always the normal stress, as I shown you that the normal stress component, this is the matter of area concern, and this perpendicular is there, and if this is my matter of this area of this matter of area is concerned, then the forces are being parallel to these things, and that's why these stresses are being formed. The single shear stress takes place on a single plane, and the shear stress is always the cross sectional area of the rivet. So if you are talking about any rivet joint, always the rivet joints are being designed on the basis of the shear stress, that how shearing is taking place. And wherever you see the shear, because you see if you see the rivets, they are always, you see two sheets are there, and they are always combining two sheets. So if we are pulling, you see and the force application is there on these two these two parts are different. One is on the top of, one is on the bottom plate. So now the point of application of this force is acted at two different axes. So definitely you see, and if you want to combine those plates, if we are putting the rivet, then always there is a shearing area is there towards those connection points, and that's why you see if you want to analyze the strength of the rivet, then always we need to design based on the shear stress, whereas the double shear takes place in the case of butt joint. So if you are having the butt joint, then you see the double shearing is there. That means you see the butt joints are always acted so that you see the area of the matter of area is concerned is twice than the rivets, and the shear stress is twice than the cross sectional area of the rivet, because you see it is applied at the two different points. So if you see this figure, then we can clearly differentiate those things, that you see now the shear failure of the rivet. So now you see here in this, we have, this is our the area of matter, this is our the plane, and this area, the top of that, this is our area of this matter of concern. So here you see now these if it is parallel, so this is the parallel part. So what we have the tau, that is the shear stress, and this is the normal, which is a perpendicular part. So we have the sigma, so normal stress. So if we want to find it out that what is the strength of these rivets are, what we need to resolve these the components, like one is the parallel, one is the perpendicular. So what is the resultant force is there, and you see by resolving those things in the resultant force SR, cos theta or sin theta, we can get the effective solution, that actually how much those like the individual as well as the combined stresses are being set up, or combined forces are being set up within this region. Once you know these things, by resolving in x and y direction, you can get the effective solution that actually how these, either the shear stress or the normal stress, are effectively concerned to the design of these kind of structures. So as we discussed in that shear stresses are always dominating in these kind of this kind of structures where the rivet as well as the butt joints are there. So if we are talking about the butt joint, in which you see, like you can see we have these two, like this is one plate, this is another plate, you see these two plates are there, and in which you see, like the force is acting. So what we did here, we simply combined these plates by these butt joints. So now if we apply these axial pulling here, like this is the shearing area, you see, where, because it will just try to pull out, but this will try to make the cohesiveness here. So here this is the effective area where shear stresses are always dominating. And you see now we are saying that this is the two butt joint. The two butt joint means you see here that here we have the two different plates. One is the this total plate which is being combined, like by both of the butt joint, these two plates you see bottom and top, okay, which is always confined, which is always binded by these butt joints. But we have these, like the separate plates. So if you apply those things here, this region is the effective region where the shear stresses are being set up. Okay, now if you go to the another point, that is you see the lap joint. In lap joint it's a pretty straight, and this is the perfect example of the shear stress, because you see here the line of action. If you see here, this is my line of action for this force. Okay, as I told you, the force is nothing but the point of line of action. So here you see this is my, like the point where the line of action of force is here, here the line of action of force is here. So if I now combine those things, so the nature of this force will try to tend this one towards this direction, the nature of force of this P will try to tend towards this direction. So we have a clockwise region motion is there, but this lap joint will try to put the resistance towards this clockwise, the motion, or I should say actually the line of action. So you see here at these portion where this contact region is there, this whole region will suffer by the shear stresses. So like you see here now, like for the single part, for either the butt joint as well as the lap joint, always there is, you see, the stresses are there. But if you go to the double shear, like in the butt joint, as we have seen, you see, like here, these are the, like the effective portions where the stresses are being well set up. These are the shear stresses, because as I told you, like these forces are there, and because of these forces, they are well parallel to this application. Means this is my effective area. You see, this is contact area. These all contact areas are the effective areas, and the force is also parallel to the effective area. That means you see here only shear stresses are being acting on these parallel forces. So we can say if we want to resolve any of the forces within this butt joint, we need to be very careful that actually how these stresses are being like taken place in this object first, and second you see which areas are the concerning areas, or I should say the effective areas where the shear stresses are maximum applied. So here you see either the first this figure or this figure, we can clearly see that these regions, either this region or this region or this region or this region, all these four regions where the contact points are there, the mating surfaces are there, these surfaces are since parallel to the applied force, these are parallel to the applied force, shear stresses are being well set up within these things, the internal intensity like of these shear forces are well set up. So we need to be very careful that actually if they are uniform, then you don't have to go for delta F by delta A. Straight away you see whatever the effective area is there, how much force is there, just like divide the force per area, you will get the shear stresses. Okay, but if you see, if we have the combined stresses, like you see, if let us say if the any other application of the force is, then we have to be very careful that actually how these forces are being acted on these objects, and then you see whether they are acting perpendicular to the area, affected area, then you have to concern the normal stress. If they are acted just like parallel as you see in this particular figure, then you need to be very careful that actually only the shear stresses are there, no need to consider the sigma value, that is the normal stresses. And if you see the final figure, that is nothing but you see again a kind of lap joint in the like the double part, then we can see here there is a straight shifting. So as you apply the force, there is as you apply the load or the force in the previous figure, you can see that there is a straight shifting of these contact regions. So this is nothing but the pin is there, so pin is now sheared. So this one was, you see, earlier as I told you, this one was the key feature was there, that actually how it can sustain or withstand the forces. So you see, if it cannot, then you see it will go up to this feature. If it can sustain, then it has to be there within this region. So this will like define the shear loading of any feature, and that's what you see. This has a good application in boiler design, because you see in boiler what we are doing here, like the lots of internal forces are coming, because of, you see, the basic purpose of the boiler is just to generate the heat. So as heat is generated, you see high pressure we are generally categorizing in various types. So if we are talking about the high pressure boilers, that means you see like the highest pressure means actually more than 400, or you see like the megapascal of the steam is to be generated within those things, either the coal fire or whatever, you see like this steam generation is there. So in that, you see, boiler surfaces are being like by lap joint, or we can say butt joint. So in these joints, because of the internal forces, you see always it tries to shear those different mating surfaces, and that's why you see like in these things, if boiler failure is there, means explosion is there, it is because of the failure of these, one of the basic reason is because of these failure of the joints. So these joints may fail, and you see like it's a clear shifting is there. So in this lecture, you see like since it was a basic lecture, you see like, so we discussed that what the forces are. You see, if we are talking about a solid like a part, then there are deformable, there are rigid bodies. In this deformable bodies, as we have discussed, that actually like how the deformation takes place, what is the like the point of application of load is, accordingly we can categorize the two basic forms of the stresses, like the normal stresses as well as the shear stresses. How the normal stresses can be acted, like what is the point of application of forces there in the normal stress even itself, that whether it is like towards the like the pulling side or the compression side, or it is a, you see like the bearing stresses. So accordingly we can categorize those things, like you see we have the tensile stress, compressive stress, or we have the bearing stress. While other thing, you see we have, if the forces are not parallel or not perpendicular to the plane, then automatically it is parallel to the concerned area. Then you see like we have to be very careful that actually since it is not on the same axis, it is on the plane, along the plane. So how they are acting, whether they are just trying to tend these objects to rotate those things or not, because always when they are not uniaxial, definitely they will just try to act at a different axis. That means there is, due to these forces, there is a chance of the object will tend to move in any of the direction, clockwise as well as anti-clockwise. So if we want to define the sign convention of these stresses, always we need to see that how these in uniaxial form or biaxial or triaxial in the normal stress component or the shear stresses, how they will like act on the object, and correspondingly see like we will define that, okay, now since these two forms of the stresses are there, one is the normal stress, one is the shear stress. In the normal stress there are, you see like this tensile, compressive, bearing, or in the shear stress side even the shear stress, torsional stress. So these are the two broad categories, and then you see like there are like bending stresses are there, which are nothing but the combination of the compressive as well as the this compressive as well as the tensile stresses. So these are the derived stresses are there, and the last one was the thermal stresses, which like due to the temperature variation they are being set up. So in that it again depends on what is the thermal coefficient of the expansion. So it's a property of the material. So this, in this lecture we basically concerned with those kinds of stresses. So in the next lecture we will just try to analyze that if you see like if these two stresses are there, then how many forms of these stresses which we need to define all those forces which are being set up within the object is necessary. Whether these two forms are okay, like you see one part is sigma, one part is tau, is well set up, or do we need more part, like you see in x direction or in y direction or in z direction, in all the directions. If we have pulling, uniaxial pulling, or the plane forces are there, like you see these parallel forces, then these two parts are okay, or do we need more forms of the stresses? So like you see like all these issues which we are going to discuss, and if they are pulling, then positive direction is there, or if we are like compressing, then the negative direction are there. So what is the basic direction, or if it just be due to this shearing part, if it trying to tend in the clockwise or anti-clockwise direction, then what is the sign conventions are there. Or if we have like the direction of the force and the area, if both are acting at the same place, then you see how you can define whether it's a normal stress or it's a shear stress. So all the sign conventions with the subscripts are there, you see, we just want to define in the next chapter. Okay, thank you.
Thank you.